So we said that energy was the driving force behind the behavior of matter. So energy is involved in chemical and physical changes. Here's an important idea. Systems with high potential energy have a tendency to change in a way that lowers their potential energy. When I held my pen out, it had high potential energy. When I let it go, it fell to a state where it had lower potential energy. This, the idea of energy reminds me of now my third son is a teenager. My experience with teenage boys. They tend to go to low energy state, right? They get up and they do things. My boys played football and basketball and all kinds of stuff, and they would go to practice and exert tremendous amounts of energy, but then they always reverted to flat out in the bed, sound asleep, right? Low energy state. Matter does that as well. So if it's at a high state of energy, it's going to tend to change in a way to go to a lower state of energy. And so it's kind of a principle of the universe, really, that things are trying to get to a lower energy state. So what that means is that objects or systems that have high potential energy are unstable. The pen, up here in midair is unstable. It wants to fall. Chemical substances have potential energy. Some of them have tremendous potential energy. The higher the potential energy of a chemical substance, the more unstable it tends to be. Think of TNT, it's so hard to say, trinitrotoluene. That's probably why we call it TNT, dynamite, right? It has a relatively high potential energy, and it's unstable. You give it a spark, and it's going to release that potential energy and change in a way that will reduce its potential energy. So TNT molecules tend to undergo rapid chemical changes to lower the potential energy. TNT is explosive. Gasoline. Gasoline has a tremendous amount of potential energy, stored chemical energy. Gasoline is unstable. So here are a couple of new words. Exothermic and endothermic. So we have exothermic and endothermic. And here we're using prefixes. Exo is like exit. It means to go out. We have an exit sign above the door. That's where we go out. Endo is a little bit like the word in. It's the opposite of exo. It's in, going in, on the inside. If you've taken biology, you may have learned about exoskeletons. A creature with an exoskeleton has their skeleton on the outside, right? So exothermic has to do with heat exiting. In an exothermic reaction, heat or energy is released. Heat is a form of energy. And so here in this diagram, we have a little graph where energy is increasing as you go up. In an exothermic reaction, the reactants start out with relatively high energy, and the products have lower energy. What happens to the energy? It doesn't disappear. It has to go somewhere. It leaves the system. So in an exothermic reaction, the reactants have higher potential energy than the products do. And as a result of that exothermic reaction, energy is released in some form. It could be in the form of light or electricity or heat, any number of things. In an endothermic reaction, the opposite is happening. Energy is being absorbed by the system. And so the reactants start off with low energy, they absorb energy, and the products have higher energy. Which one of these situations is more likely to happen spontaneously? Exothermic or endothermic? Exothermic. Because we talked about how matter with high potential energy tends to change in a way to lower its potential energy. And so exothermic reactions more commonly occur by themselves without much help. There are also those spontaneous endothermic reactions. Any questions about those terms? Exo and endo. Okay, let's identify each of these changes as exothermic or endothermic. Now what we have to remember is that we're thinking in terms of the matter that is reacting. And is energy coming out of that or going into it? Because in the whole universe, the energy isn't changing. And so we describe a system, which is the part of the universe that we're looking at, and we could describe that any way we want. And then we have the surroundings, which are everything else. So wood burning in a fire, the wood is what we're looking at. Is the wood giving energy out, or is it taking it in? It's going out. When, we had a fire in the fireplace last night. I hope it was a burn day. We forgot to check. It's one of those manufactured logs, though, so it burns very cleanly. But the kids, are all fascinated and come up, and you feel the heat energy coming off when wood burns. So wood burning is definitely an exothermic process. How about ice melting? Think about the ice. Is it giving energy off or is it taking energy in? It's taking it in. If you put an ice cube in your hand, it feels cold, doesn't it? And your hand gets colder. What's going on there? Transfer of energy. There's heat energy from your hand is going into the ice and causing it to melt. And that's why it feels cold to you, because you are losing energy. How about water freezing into ice? That one's a little harder to think about. Water freezing into ice. Sometimes it's helpful to think of the opposite process. Freezing is the opposite of melting, right? And if melting was endothermic, then freezing must be exothermic. That's not nearly so obvious as the wood burning. Wood burning, we feel heat giving off. How do you get something to freeze? Put it in the freezer, right? What is your freezer doing? Your freezer is pumping heat energy out of the compartment. I think this has a very interesting application here in the valley. We get a frost. They're predicting a freeze. What do the farmers do? Well, you cover your stuff if you can, but you can't cover a whole field of oranges. You water, right? Why do you water? Because water freezing is an exothermic process. In order for the water to freeze, energy comes off. So the water being present there moderates the temperature of the field. And we'll learn later that water freezes at 0 degrees Celsius, and the temperature does not fall below 0 until all the water has frozen. And so as it's freezing, energy is coming out and it's keeping the air around it at 0 degrees Celsius as well. So, of course, the farmers talk about degrees Fahrenheit, so 32 degrees Fahrenheit. And then the wind machines, one of their functions is to take this warmer air that's down by the water, seems cold, but it's relatively warmer than maybe what's up above, and move it around. And take this warmer air, 32 degrees, down on the ground and bring it up. And it's amazing, just that little bit can keep the oranges from freezing. So it's pretty cool. So water freezing is actually an exothermic process. It gives off energy. How about natural gas burning? Exothermic. You see that if you have a gas stove. You light the gas, what happens? It gets hot, right? Bunsen burners, they get hot. Any questions? So this is the sort of thing that you should be able to do for an exam question. And again, like with the ice, with the water freezing, if it's just not real clear what it is, try thinking about, well, what would it be if we did the opposite? And that can be helpful in deciding.